Good afternoon, everybody. Welcome to lecture number 8 of the Summer School, SSDS Summer School, organized by CREDDS. Today, we are happy to welcome Professor Frank Zok from the University of California at Santa Barbara, who will be telling us about experimental techniques for dynamic deformation of solids. Frank got his PhD from McMaster University and is currently a professor at UCSB. I only just read on his website that he is the 2020 winner of the Nadai Medal from the ASME, which is a big deal. So congratulations for that, Frank. He is a fellow of the American Ceramic Society and has wide-ranging interests in design, fabrication, and performance of materials and structures. Today, he'll be telling us about one of the areas of his expertise and ongoing research, which is in dynamic testing of materials, and in particular on the experimental methods for doing that. So Frank, thank you very much for joining us.
All right, great.
And I believe now you should be able to throw up your slides and we'll proceed from there.
All right, terrific. Thank you, Michael, for that kind introduction. For the students returning, both young and old, welcome back. I'm glad I can have this opportunity to talk to you about some aspects of experimental techniques for dynamic deformation of materials. So Michael asked me to talk on this topic, and what I thought I would do, rather than trying to be very comprehensive on techniques, is to focus in on a smaller number and focus in some parts of this on the underpinning theory. I think it's essential that in order to understand and fully exploit any experimental technique, you really need to understand the underlying theory, even at a very rudimentary level. And so one of my goals today is to go through a few of the very elementary derivations associated with dynamics of stress wave propagation. I think for most students that have had a traditional background in material science and engineering probably haven't had formal training in this. And I think there's no better substitute for learning the fundamentals than actually deriving some of the key equations from scratch, using very basic principles of force equilibrium, compatibility, momentum conservation, mass conservation, etc. So with respect to the techniques themselves, I'll focus on two groups. One of them, the first group you're familiar with. This includes the Kolsky bar, also known as the split Hopkinson pressure bar test, and the plate impact test. Both of these involve controlled impacts of bodies in ways that produce controlled stresses. And usually here we're striving for achieving either a state of uniaxial stressing or of uniaxial straining. Okay. Now, the second group are ones that are less commonly used, but I thought I would include them because they are useful in many instances where the more traditional tests like the Kolsky bar, the plate impact, don't give all of the requisite information about dynamic response of materials and structures. And the latter two include small projectile impact and methods for simulating blasts in the laboratory. That is, imposing pressure time histories that reflect those that you would get from a blast situation. Okay, so let's start with the first two of these. Now, the main thing that distinguishes these two different tests is the strain rate range over which you can access. Now, looking at the full strain rate range we have here at the bottom, at low strain rates up to something like about 1 per second, we have servohydraulic machines. Virtually all labs are equipped with machines of those type. There is then a gap, more or less, in strain rates from about 1 to 100 per second. There are specialized machines that can do that. But as it turns out, I think in most cases of interest, there's not much that goes on, much difference in material behavior, going from about 1 to about 100 per second. The Kolsky bars find this range here of about 100 to about 10,000 per second strain, right? And this is the test that's used most frequently for characterizing dynamic mechanical properties. And you can scale these things down in order to access higher strain rates. That's a very specialized art. And then we have flyer plate impact tests, which get us to strain rates of 10 to the 5, 10 to the 6 per second and beyond. So a couple of schematics just to show the machines that are used. So this is the Kolsky bar. There are 3 bars involved in the test. There is a striker bar, there's an incident bar, and a transmitted bar. The specimen sits between the incident bar and the transmitted bar. The idea here is you launch the striker bar at a given velocity from a gas gun. It impacts, it collides with the incident bar here. The bar is in a series of guides and bearings so as to maintain alignment and to allow free motion axially. So as this striker hits the incident bar, it produces a stress pulse at this end here. The stress pulse runs through. It hits the specimen, goes through the specimen. A part of that stress is reflected back into the incident bar, and a part of it is transmitted into the transmission bar. Okay? All right. Now, the other type of test, the flyer impact test, is in some ways analogous in that we're taking a flyer. In this case, it's a flyer plate. And in this case, it's mounted in a carrier called a sabot. This allows it to be launched through a gas gun and to remain well aligned so that the surface of the flyer plate is coplanar with the surface of the target plate. So it's launched in a gas gun. The flyer hits the target plate, and in this case, the target is necessarily thin in this direction and large in this direction. The aspect ratio, if you look at the diameter to the thickness, is on the order of about 10. Okay? Now, importantly here, in order to get any useful measurement, we need to measure the back face velocity using an interferometry method. It's called VISAR, which I'll return to later. Okay? But this gives us a direct measure of the free surface velocity of the atoms on this back face. From that, we can get the particle velocity, and from the particle velocity, we can get at the stresses within the body. Okay, so let's start with the Kolsky bar. Here is a computer simulation showing what happens when you have this collision. So this is now inverted. The striker bar is coming in from the right. It strikes the incident bar. As it does so, it produces a stress pulse both in the striker and in the incident bar. And because the two materials are usually the same and they're of the same diameter, you have equal pulses, compressive pulses, produced in both the striker bar and the incident bar. Okay? So the stress wave travels down the incident bar, and usually midway along that incident bar, we have a strain gauge to measure the strains in that bar. And knowing what the modulus of this material is, we can, from that strain, determine the stress in the bar, and from the area, we can then get the force that's being transmitted through the bar. So the wave continues through in more or less a planar fashion. It hits the target, a part of it reflects back as a tensile wave. It goes through the specimen, and a part of it is transmitted through the transmission bar. Now, the transmission bar also has a strain gauge mounted on it at the midway point, somewhere here far off on the left. Okay? And so with this kind of test, we're measuring strains in the incident bar and in the transmission bar. And from that, and from just a very rudimentary analysis, we can get at everything that we want. We can work out the forces that are acting on the specimen, both on the front side and the back side. We can work out the strain rates that the specimen is experiencing. and the total strain that the specimen is experiencing. Okay. All right. So this is where I think we need some of the rudimentary mechanics underpinning dynamic tests. Okay. I'll go through some of these derivations. I hope you'll follow along with them, those that haven't seen this. I think this is really quite essential in understanding where a lot of the interpretation and analysis of Kolsky bar tests come from. Okay. And there are essentially four things that one needs to think about. One of them is just elastic wave propagation in a one-dimensional sense. And we'll look at this in the context of long, slender rods and in wide plates. The first of them giving a uniaxial stress condition and the second giving uniaxial strain. And as you might imagine, the first one here pertains to the Kolsky bar, the second to the plate impact test. The other thing to understand to some extent is the reflection and transmission of elastic waves across boundaries. And boundaries can be between two solids, or they can be between solid and a vacuum. The other thing to appreciate is the nature of collisions of elastic rods and the stresses that are produced. And finally, the propagation of plastic waves or shock waves. Those become particularly important in the plate impact experiments. Okay, so let's start with elastic wave propagation in a long, slender rod. So this is the problem we set up. We imagine we have a long rod. We put a pulse into it on the left side of it. This material's got some density rho, modulus E, and the particle velocity is denoted here as VP. And what we do here, importantly here, we assume that this is a uniaxial stress. Put it another way, we're neglecting any radial inertia. Okay? We recognize that when we apply a stress in this direction, the x direction, horizontal, we get a corresponding Poisson strain in the transverse direction. We neglect the inertia associated with that Poisson strain. So we have a uniaxial stress propagating along the rod, and we analyze some incremental volume of thickness dx of area A. And so we set up the usual force balance here. We say that there is some force acting on the left side of this incremental volume. It's the stress times the area. And there's some different force acting on the other side, some sigma x plus di sigma x dx times the area. And then we just write the equation of motion, F equals ma. So the force difference between these two is just A times the rate of change of the stress with x times dx. The right side here is mass times acceleration. This term here, rho A dx, is the volume times the density, which gives you the mass. And this is just u double dot, or the acceleration. F equals ma, very simple. If this is an elastic wave, we combine this with Hooke's law, and we say that the axial stress is related to the axial strain through the Young's modulus. And in turn, we can write the strain in terms of a displacement gradient. If we substitute that back into our equation of motion, we get this all-important so-called wave equation, which simply says the modulus times u double prime, second derivative with respect to x, is equal to rho times u double dot. This is the derivative of displacement with respect to time. And this is really the basis for much analysis of elastic wave propagation in solids. Now we can take it one step further, and we can also look at the conservation of momentum. There is an impulse put into this volume element. It's a force through it times a time. That force is sigma x times a over some increment of time dt. That has to balance the momentum within that volume element. That's just the mass times the velocity. So the particle velocity is Vp. The mass is rho times the volume of that element, A times dx. Rearranging, we get then that the axial stress is rho Vp times dx dt, where we recognize that dx dt is simply the speed at which the wave is moving through the body. That's denoted here as C naught. We can equivalently write this stress, taking these two, the rho and the C naught out, and we call that product the acoustic impedance. so that the stress is proportional to the particle velocity through this proportionality, notably the acoustic impedance. Okay. Now, if we rearrange the results above, we can solve for the wave speed C0, and with a couple of simple steps of algebra, we come to this result here where the wave speed is the root of E over rho, a result that almost all of you have seen at some time, though you may not have seen the derivation of it. We can then rewrite our wave equation using this relationship between C0 E and rho. We plug that into this, and we get that U double prime is just U double dot over C0 squared. Now, when we get into wide plates, the problem changes in the following sense. If we imagine hitting it with a pulse on this face, and we look at some increment of volume slightly ahead of that face, at a distance that's small compared to the lateral dimension, we find that for all intents and purposes, the strains in the vertical direction and in the outer plane direction are zero. Okay? So we produce a state from the stress of uniaxial straining in the x direction. We can go through the same analysis as we did on the preceding slide, and we define here an effective modulus, if you like, which is the ratio of the axial stress to the axial strain. And this is defined when the two transverse strains are identically zero. If we use that in place of Hooke's law in the preceding slide, and we combine it with the equation of motion, we get this form of the equation, the wave equation, where now the Young's modulus is replaced by this effective modulus E tilde. And in turn, we find, if we continue the analysis, that the wave speed, CD, this is now what's referred to as the dilatational wave speed, is the root of E tilde over rho. Okay? Now, what is E tilde? Well, we can work this out from generalized Hooke's law. We write, firstly, the strain in the x direction, that's the horizontal direction, in terms of the stress in the x direction, in terms of the two stresses in the other direction, sigma z and sigma y, through the usual statement here, Poisson's ratio nu, Young's modulus E. We recognize that the two transverse stresses are the same, so we can lump them together. We similarly write an expression for the strains in the y and the z directions in terms of the stresses and the Poisson's ratio and the modulus, and we set that equal to 0. So rearranging this last equation, we solve for the two transverse stresses, sigma y and sigma z. They're proportional to the axial stress sigma x through this proportionality constant, nu over 1 minus nu. Now, if we plug that in turn back into here and rearrange, we find that epsilon x is proportional to sigma x through this whole grouping. And from that grouping, if we take the ratio of sigma x to epsilon x, that gives us E tilde. And E tilde then is just the Young's modulus times this function of Poisson's ratio. And so when it comes to the dilatational wave speed, it's similar to the long rod wave speed, with the exception that it's got this additional function here of the Poisson's ratio. Okay. This is it's not an insignificant effect, but it's not a huge effect either. We're looking at differences between the two wave speeds of about 20% for typical Poisson's ratios. So that's elastic waves in 1D. The other thing to recognize here is what happens when waves cross boundaries. And so here we consider a case where we got, say, two thin long rods, one of material A, one of material B, and they're glued together at the interface. They each have their respective mass density, Young's modulus, wave speed, impedance. And what we do now is we consider what happens when this stress pulse reaches this interface. Now here we make use of two conservation equations, essentially. Firstly, we set the forces at this boundary in material B equal to the forces in material A. There has to be a force balance at that interface. In this case, we can generally write that the incident stress sigma I plus the reflected stress at this interface, this will come back the opposite sign usually. The sum of those two has to equal the transmitted stress. We also invoke continuity of velocity at that interface. And so we write that the particle velocity due to the incident wave plus the reflected wave has to be equal to the velocity due to the transmitted wave. And we can write the particle velocity in the way that we saw in one of the preceding slides. If we combine these equations, and that's all you need here, is you can get immediately at both the reflected and the transmitted stresses normalized by the incident stress. And so what you find here very simply is that the reflected stress is simply the difference between the acoustic impedance of material B and material A divided by the sum of the two acoustic impedances. The transmitted stress is twice the acoustic impedance of material B divided again by the sum of the two acoustic impedances. Okay? Very useful result in understanding how waves behave at boundaries. A few limiting cases, just to ground ourselves. If we have a free end, that is, material B has no modulus, it's just air, then what this tells us is that ZB is going to be 0 here and here. So we're going to get minus ZA over ZA. And so the reflected stress is just -1 times the incident stress. What that tells you is that if you have a compressive wave coming down a bar, when it hits a free end, it reflects as a tensile wave, canceling that compressive wave. Here also, our transmitted stress, because ZB is 0, is 0. Now, another limit is when we have a rigid end. So if material B has infinite impedance, then we find that the reflected stress is 1 times the incident stress. That is, it comes back as a compressive stress. And so the stress at that interface in material A doubles. One other limiting case, a trivial case, is when the two materials are the same. And if you look at the equations, if ZB is equal to ZA, then the reflected stress has to be 0. And the transmitted stress has to be equal to 1 times the incident stress. Okay. All right. Now, collisions. So here we consider what happens if you have a striker bar, for example, of material A launched at some velocity V. And in general, we can think of this material having its own density modulus wave speed impedance, and it impacts material B with its own set of properties. Here again, we just go through the continuity equations. We write that upon impact, the interface velocity has to be equal to the velocity of this rod initially, minus the particle velocity in A at that interface, which will be acting in the opposite sense. You set up a compressive wave in material A, which causes those particles to start to move to the left relative to the interface. And that net velocity, this is the net velocity of the interface at A, has to be equal to the particle velocity in B at that same interface. Okay? Continuity, it's simple. We also invoke a force balance where we say that rho CV on one side is equal to rho CV on the other. And we further substitute in this expression for the velocities into here so that we can write the stresses in terms of one of these velocities. So we can then solve, for example, for the particle velocity in material A. And you can see what we get here is the acoustic impedance of B divided by the sum of the acoustic impedances times the initial impact velocity. If we then combine that with the stresses, with the stress equation, rho CV, then we find that that interface stress becomes, a new result now, it's the product of the acoustic impedances divided by the sum times the impact velocity. This is another key result. Limiting cases. If material B is 0, then there is no interface stress. That's a trivial case. If the material B is rigid, it has an infinite impedance, then the interface stress is just you can see that this will cancel out. So you just get, this is just going to be ZA times V. And that just becomes rho CV, where V in this case, notably different from the preceding slide, is the initial impact velocity. In this case, it turns out to be equal to the particle velocity. Now, for cases of practical interest, like in the Kolsky bar, the two materials are the same, so they have the same acoustic impedance. So we set ZA equal to ZB equals Z. And here we find then, if we plug those into here, we get a factor of 2 in the denominator. And so here we find the interface stress is just rho CV, uppercase V, divided by 2. Okay? And this is the stress that we calculate when we do a Kolsky bar type of test. All right, one more topic on theory, plastic wave propagation. So let's consider now the case we were considering earlier, where we've got a long slender rod that's hit with a pressure pulse. We're going to analyze an incremental volume. Only now we're going to consider a case where we've hit this hard enough that we've exceeded the yield stress. And let's imagine that our axial stress-strain response looks something like this. Okay? There's our yield point, and we subsequently have a hardening rate that's lower than the Young's modulus. We go through the same sort of analysis. We write the equation of motion. That's identical to what we had before. In this case, d sigma dx, we cannot write in terms of Hooke's law because the material is no longer elastic. But we can write it in terms, just expanding this d sigma dx, in terms of the hardening rate, d sigma x d epsilon x, times the gradient d epsilon x dx. And in turn, we can write the strain gradient in terms of the displacement. So we get here the second derivative of displacement with respect to x. We combine that with the equation of motion, and we get a form of the wave equation that's very closely analogous to what we derived earlier. Only now the multiplier on u double prime is the instantaneous tangent modulus, d sigma d epsilon. Oh, there's a superfluous dx in here, by the way, that shouldn't be here. And that's going to just be equal to rho times u double dot. Okay? So if you go through this analysis, what you find is that the plastic wave speed is given by the tangent modulus at the appropriate strain divided by rho, the root of all of that. So what happens as a practical matter is this. If we strike an elastic plastic bar in this fashion, what we will find is that there will be an elastic wave that travels down it. If we were to look at the strains as a function of position, at a speed of c naught, so that at some position c naught times t, this is going to be the elastic wave, and it will be at a strain equal to the yield strain of the material. Okay? So the material is elastic right at that front. And in its wake is the plastic wave, and this is also moving to the right, but it's moving at a much reduced velocity. Okay? The important point to recognize here is that the reduced tangent modulus reduces that plastic wave speed, and hence the plastic wave always trails the elastic wave. Now let's consider what happens when we have 1D straining. And this is the basis for the plate impact test. So in this case, if we have 1D straining, we find that our stress-strain response looks like this blue line. We reach a critical stress here. It's referred to as the Hugoniot-elastic limit. It's a fancy term for the yield stress in 1D straining. And typically, the rule of thumb for typical Poisson's ratio, it's about twice the uniaxial tensile yield strength. Then the curve, in terms of the nominal stress strain, looks something like this. Okay? It's concave up. And this is because the shape of this comes about because of the fact that you're constraining epsilon y and epsilon z to be 0. So in this case, if you hit a plate like this, you will find, first of all, if you hit it at a stress that's below the HEL, then you just get an elastic wave propagating down the bar. If you hit it at a higher stress, one that produces a stress at point A, you find you have two waves. You have an elastic wave, so that would be at this point here, and it will be moving at the dilatational wave speed. So this position, the position of the elastic front, will be at CDT. And then in its wake will be a plastic wave, or strictly it's a shock wave. And it's going to be moving at a different velocity. And that velocity will be dictated by the slope of the line from the HEL to point A. So what happens in this case is that you don't follow an equilibrium path along this curve. This is sometimes referred to as the Hugoniot curve. But instead you jump from the HEL to this point here. Okay? Now, the reason you have that jump is because the tangent modulus here is greater than, say, the tangent modulus here. And so the larger amplitude plastic wave wants to travel faster than the lower one. If you increase the stress further, you get to B. You would get a curve sort of like this, but at a higher stress level. And if you hit it hard enough, what you find is that you don't even see the HEL. What happens is you have a shock occurring and you jump from this state to this state, not following the equilibrium path. And so what you find in this case, if you were to look at the strain as a function of position, you would get that it would be uniform in the wake. It will be moving at the shock speed. So the front will be at CS times T. And there, let me emphasize, there'll be no information about the Hugoniot-elastic limit. All right. With that rudimentary mechanics, we can go about analyzing everything about the Kolsky bar. Okay. We have, recall, a collision between a striker bar and an incident bar. We have transmission of stresses across the boundaries with the specimen. We have transmission of, and we have a reflection there as well. We have transmission of that stress within the transmitted bar. So we can go through and analyze this using the equations we've developed. We find the impact stress. This is what we saw when we looked at collisions. It's just rho C times V over 2. This is the incident strain is just that stress divided by the modulus, which you can show is just the velocity over 2 C naught. And the time of the duration of the pulse is given by this equation. It's twice the length of the striker bar over C naught. This comes about incidentally from the time that it takes for the wave that's developed at the striker bar edge here to propagate backwards, reflect off this back face as a tensile wave, and come back to the front face. Okay? So it's the time that it takes for the wave to travel from here to here to here. And that's that time. By the way, for those of you who do tests of this type, should be very cognizant of this equation here, because it tells you what stresses you're going to impart on the striker bar. If you put in typical numbers for steels that are used, if you put in a row of about 8,000 kilograms per cubic meter, a wave speed of 5,000 or so, or 5,500 meters per second, and you put in an incident velocity of, say, 50 meters per second, you find that this stress is about 1 gigapascal. Okay? Now, you got to be careful in doing these experiments, because if you exceed the yield stress of the incident bar, you cause it to deform plastically, you can be sure somebody's going to be unhappy with you. Even the best Mar-aging steels that are used for these applications have yield strengths in the range of maybe 1.5, maybe to 1.7 GPa. And so you want to stay sufficiently below that yield stress in doing experiments of this type. Okay. All right, well, we can go through this analysis and continue this analysis to work out what the strain rate of the specimen is. It's going to be, this is effectively the displacement rate divided by the specimen length. The R here corresponds to the strain in the reflected strain in the incident bar. We can then work out the forces both at the incident bar specimen interface. That would be this interface here, based on the strain gauge measurements here. And we can work out the forces at the transmission bar specimen interface, which is given by the strains in the transmitted bar. Okay? Now, if we're in equilibrium, if the specimen is in equilibrium, which it isn't always, then these two forces have to be the same. And that, in turn, if we set these equal to one another, we see we get this relationship between the sum of the incident and reflected strain in the incident bar and the strain in the transmission bar. Okay. From this, we can further, by looking at the displacements from the strain measurements, we can work out the specimen strain. And then we can work out the specimen stress in a number of ways. We can work out either the back face stress, which we've called it's F2 divided by the area of the specimen. We can work it out in terms of the force on the incident bar specimen interface. And again, if you have equilibrium, these two should be the same. Or you can take the average of those two. Okay? Now, it's important to look at both of these forces because they tell you whether or not you have indeed achieved equilibrium. In order to achieve equilibrium, you necessarily want a specimen that has a relatively high wave speed and is sufficiently short so that the time of transmission across that specimen is very short. So here's an example of a good test. This is of a stainless steel. The results here are for both the strain rate, that's this curve here. These oscillations are normal in these types of tests. That's a good test. If you look at the one wave solution, this is using the back face stress, you get the solid line. If you use the front face stress, you get the dotted line. Okay? And the fact that these two are almost the same is just confirming that indeed you're achieving equilibrium. Whether or not you want to take the average of these two to get the average force on the specimen, well, it doesn't really matter. You're going to get essentially the same kind of result. Now, if you hit a material that's got a low acoustic, it's got a low wave speed. Take lead, for example. It's got a very low modulus and a high density. So the waves travel very slowly through lead. What you now find is if you use the one wave solution, this is the back face stress to get the stress strain curve, you get the solid line. And if you look at the front face stress, this dotted line, you see these huge oscillations. And that tells you that the specimen is not in equilibrium during this test. Okay? So you want to do something different with the test, or you have to be cognizant of this in interpreting your experimental results. Okay, let me just show you a quick video of an impact. And this is kind of if I can get it to play. I don't think I managed to. It's not. That one doesn't seem to be working. Let's try the next one. Okay, let's do this one. So now, as with any kind of standard mechanical test that we do quasi-statically, we can use various strain measurement techniques on the specimen itself. And this is useful because in cases where your strains are not uniformly distributed along the length, it's useful to get the direct strain measured on it rather than just using the displacements that you calculate from the strain gauges. Let me just try to get out of here for a second. Something's frozen up here, I'm afraid. It was working just a moment ago, and now it's not. It's going to go directly to YouTube. Can you see the YouTube page? Oh, that's not even the right video.
Nope. I think you would have to change your screen sharing.
Yeah.
Because you're.
Good point. Yeah, I'll skip it, Michael. These videos aren't that critical. The point there being that you can actually measure the strains directly on the specimen using non-contacting digital image correlation. Now, we can turn the test around, this Kolsky impact test, and do this in tension. You simply launch the projectile or the striker in the other opposite direction. You hit a flange to send a tensile pulse. And you go through the same kind of analysis to get the specimen strains. So these are just a couple of short videos that show what happens. I don't know if you can hear the volume there. These things make a bit of a bang when they're tested dynamically. Here are a couple of other videos showing the DIC measurements. In the left side of titanium alloy, and you can see the strain distributions you get there. Here's an example of a plastic film where, because of the very large deformations, you have non-uniform straining, and where the information from the strain gauges on the two bars does not give you a complete picture of the local strains along the specimen length. Now, here's yet another example, which is useful when you have some sort of localization phenomenon. So the strains are uniform up to some point, but then you find that the strain localizes within a band here. This is probably a thin metal sheet, I think. And information about strain localizations are never measurable from the strain gauges that are on the two bars. We can also do this in torsion. I've got a video showing us, which I don't know if we'll play. It uses a torquing device to, we might have success here. Okay. So this is an example, dramatized, of course, showing a torsion Kolsky bar test. And what happens here is that one end of the bar is torqued. It's clamped at another location. The clamp is then released so that this torsion gets transmitted down the bar. And then the cameraman runs at about 5,000 meters per second to get to this point, and he captures this. Okay? So this is a thin-walled metallic tube. And with tests like this, you can do very high rate, very high strain, essentially pure shear tests on metals. Okay? All right. Flyer impact tests. So as I said before, this is analogous to the Kolsky bar test, where you launch a sabot with a projectile material here and a target material here, and you ideally want to measure the velocities on the back face using this visor system. It's the velocity interferometer system for any reflector. Okay? This was developed by Lynn Barker and others back in the 70s, and it's really transformed the use of these kinds of tests. Okay? These are really difficult tests to perform well. You have to have just absolutely perfect alignment. You have to be able to time the visor so it's activated exactly when the contact is made. It's far more critical than in the Kolsky bar test. So as we noted earlier, the stress-strain response of a material under uniaxial straining has the shape here, and that is then manifested in the free surface velocities we measure on the back face. Okay? Those free surface velocities are related to the particle velocities by a factor of 2. There's a factor of 2 there because of a reflection. That's a detail. In any event, what we find is that we get free surface velocity versus time curves of the following form. If we hit the plate at a sufficiently low velocity, then we get just an elastic wave. The wave arrives at some time here, given by the thickness of the specimen and the wave speed, the dilatational wave speed. And then you have a constant free surface velocity, and from that you could work out what the elastic stress was. If you exceed the HEL, what you find is that initially you get a two-step jump. You get a jump from here to here. This is the HEL. And then you have a constant free surface velocity for some period of time. And this is while you just have the elastic wave. And then you have a jump where the plastic wave shows up. Okay? And so this is the kind of jump that you would get at point A. If you increase the impact velocity and hence the impact stress to even higher levels, what you find is that the HEL usually doesn't change very much. But what you find is that because of this larger jump here, the shock speed is greater. That wave arrives sooner than it did for case A. And you get a higher level here, a higher free surface velocity, which corresponds to a higher stress. If you hit it hard enough, you jump straight from here up to here, point C. And what you find is that the speed of that's going to be proportional to the slope of this line, or that's going to be the pertinent wave speed, shock speed. And so it actually shows up before any precursor elastic wave. So you go straight from here, you shoot up, and you go across. And in doing so, you get no information about the yield stress, the Hugoniot-elastic limit. Okay? So these are typically what the results look like. The other piece of information that you can get from these types of tests is the following. If you have a free surface on the back of the target, compressive wave that comes in reflects as the tensile wave. You get a release wave from the impacting face when the stress in the impactor goes to 0. And you have a tensile wave that comes back, and you design the experiment so the tensile stress is the maximum near the middle of that target specimen. What happens then is you get a spall forming there. You essentially form a free surface where you get then other wave reflections. And this is manifested by this type of curve where the velocity of the free surface undergoes this so-called pullback velocity. It dips, goes back up, plateaus. And from this change in the velocity, we can work out the tensile stress that gave rise to spallation. So we can work out the Spall strength. Okay? And to get all of this, you really can just work through the analyses that we presented earlier. So these are some real results. This is for magnesium, an anisotropic material, somewhat anisotropic. These are for two different orientations of a cold rolled or an extruded rather magnesium alloy. And so these are curves for progressively increasing impact velocities. You can see here in these three experiments, you can see the Hugoniot down in here. You can see that the response here doesn't depend too much on the impact velocity. You have these jumps to higher free surface velocities as we increase the impact velocity. And we also see this pullback phenomenon associated with spallation. Here, a corresponding set in another orientation. And you can see in some of these cases, you're getting very high pullback velocities. And you can use tests of this type to study then the mechanisms of spallation. You can perform tests with different impact velocities, and you can then start to, from those interrupted tests, monitor the state of damage within the center of the plate. In many cases, this is due to ductile void growth. In other cases, like this Armco iron, it's due to microcracking. Can be used also to study polymers. This is a crack that was formed in polycarbonate. Okay, So we're going to switch gears, and I realize I'm running a little low on time. So I'll probably skip over a few of these. So here we're interested in probing materials through impact with small penetrators or small projectiles. But the idea here is that in some cases, like when we're trying to characterize ceramics, we can't get all of the information about the stress strain, strain rate, fracture response from the standard Kolsky bar or plate impact test. In ceramics that are of interest, for instance, we have at least 3 different modes of inelastic deformation. We can have lattice plasticity, dislocation plasticity as we have in metals. You could also have twinning. You have microcracking. And once the microcracks link up, you get essentially full comminution and you get subsequently granular plasticity. Okay? And so this is just an example showing the nature of this microcracking and granular plasticity in an armor alumina. I won't get into the details of this, except to point out here that all of the grain boundaries in this material beneath this indenter have undergone extensive microcracking. Okay. Now, in this case, the form of the constitutive laws are complex, far more complex than they are for metals. We need to think about, this is in terms of in stress space, this is the equivalent stress, this is the mean stress. And we find there are different domains of cracking, one where we have the cracks are closed and you don't get any sliding. You get another domain where the cracks are closed, but they can still slide and grow. And you get other regimes where the cracks are fully open. Okay? And we can analyze these problems using standard fracture mechanics analyses. And from that, we can start developing the yield surface or failure surfaces in stress space. Okay? Those correspond to failure initiation. These curves then evolve with plastic strain as the damage goes up. And eventually, once the damage reaches unity, when it's fully comminuted, you then have to switch to a different type of constitutive law. Like this is a Drucker-Prager granular plasticity law. Okay? So there's a lot going on here, and you have to keep track of the sequence of damage events and plasticity, granular plasticity, as well as the lattice plasticity. And you can't get all this information from the standard tests. So one of the ways we can start teasing out some of these processes and analyze them is by taking tiles of the material, embedding them in a constraining fixture, and hitting them with small projectiles. When we section them, we get various types of damage patterns at varying velocities. These are from about 300 to about 800. And we can then begin to analyze the extent of the damage beneath the impact site. And we can study the mechanisms. We actually get, in some cases, bands of damage emanating from this damage zone. You get a comminution process occurring locally. There's a lot of interesting stuff that goes on that we'd like to understand. And we can then use those types of observations along with finite element simulations using the constitutive laws that I referred to earlier. And if those constitutive laws are well calibrated, you find that the simulation of the damage zone can match the experimental observations rather well. In this case, we also checked the constitutive law using a plate impact experiment. And indeed, we find that the model predictions that's given by the red line matches the experimental results remarkably well. Okay? But there are a lot of these damage mechanisms that you simply could not learn about from just a plate impact experiment. There are other types of impact experiments we can do where we take a plate of the ceramic and we hit it with a projectile at sufficiently high velocity so it penetrates through the plate. And this starts to give us information about the nature of the plume of damage that comes out the backside. And this becomes important subsequently in understanding how we design back faces for ceramic armors in order to mitigate the pressures associated with these plumes. And here we show some numerical simulations at the appropriate times for impacts at these velocities. We can also do these with tri-layer systems, begin to understand something closer to a real armor system where we have a steel plate on the front, a steel plate on the back, ceramic in between. We hit these clamp plates with a projectile, and we can interrogate the system subsequently in various ways. One of them is through the use of profilometry. So we can take this back face, the back sheet, and we can map out the displacements after the test is complete. This gives us ultimately some measure of the efficacy of the plate in catching the debris from the fragmenting alumina. And again, here we can compare the measurements with simulations. These will have to be done through finite elements, but we now have a constitutive law that we believe is calibrated and which can indeed be used in combination with the constitutive laws for the metals themselves to predict the response of these sheets in a much more complex type of system under dynamic loading. Oh, here's yet another case. This is from Vikram Deshpande's group. You know, when you're testing materials like Dyneema, this is a fiber composite that is just horrendously anisotropic in every respect, in terms of its elastic response, in terms of its strength, in terms of its fracture response. There are few standard tests that can be used to fully tease out all of the pertinent mechanisms. For this, again, we can use projectile impact experiments to learn about what's happening in combination with finite element simulations. Okay, in the remaining time, I'll just talk briefly about blast simulators. As I mentioned at the outset, we are interested, particularly if being in an academic institution, in trying to apply loads to structures that mimic the pressure time histories associated with an explosive event. Okay? So here we're often interested in managing not the stresses as we do with a hard impact, but rather in managing the momentum. Okay? So we're interested in the pressure time history associated with the loading, and that pressure is usually applied broadly over a large area rather than locally as you have with a projectile impact. One of the ways to simulate this, and this was developed by Vikram Deshpande and Norman Fleck, both at Cambridge. This is a very clever way, where what you do is you launch a foam projectile onto your target. What happens when you launch a foam projectile and it strikes a target, in this case it's a solid, it's a rigid target, and this is a foam projectile coming out of a gun barrel. It hits the target and it immediately begins to crush at that interface. And it essentially collapses on itself over time because of the momentum. And what you find then, if you measure the force time response, this bar here being instrumented, is you get pressure time histories which you quantify and which you can relate to both the yield strength of the foam as well as to a hydrodynamic term which depends on the impact velocity. So this we have found to be a very useful way of looking at a pseudo-impulsive type load in understanding structural response. You can readily change the response by changing the relative density of the foam, the impact velocity, and the length of the projectile, of the foam. Okay? All right. So here's one example where we used it to study the response of sandwich beams with a honeycomb core. And the images in the top right show a series of, these are a series of images just before impact of the projectile foam. This foam is much larger than you can see here. It's probably goes out to about here somewhere. And you can see over time how this this clamped beam bends, all right, deforms. And so now again, we can use these kinds of impulsive loadings to begin to understand how to model the response of these sandwich beams subject to these types of loadings. And we can do that for sandwich panels with various applied impulse, as well as comparing it to a baseline solid plate. And we can then also compare the experimental results to numerical simulations in order to get a better understanding of the nature of the deformation that gives rise to the displacements on the back face. Okay? So this, I think, is a very clever way of doing this, of getting impulsive loads without actually having to use explosive devices. Okay, I think I'm sort of on time. With that, I'll pose a couple of homework problems, one conceptual and one a simple calculation. So the first problem to consider is this. Compare and contrast the pros and cons of the types of tests we discussed here, notably the Kolsky bar, the plate impact, and the small projectile impact test. Okay? So that's the first problem. The second problem is a simple calculation, and it involves collisions and wave propagation through elastic bodies. So here, let's imagine you have an aluminum bar. It's bonded to a steel bar. They have the same cross-sectional area. You then apply a pressure pulse to the free end of the aluminum bar, so magnitude P naught, and we leave it there for duration T naught. You could get this by, for example, striking it with a striker bar. So then that pulse is sent along the aluminum bar towards the steel bar. And the question then becomes, what happens at the interface when the wave hits that interface? And so the problem here is to calculate and sketch the stress distributions along the bar at time t equals 0, defined at the instant at which the incident pulse reaches that interface, and a short time later, a time of t naught, of 1/4 of t naught. Okay? And this, as you can imagine, makes use of the kinds of solutions we talked about earlier with respect to the transmission of stresses at interfaces between materials with different acoustic impedances. All right, that does it for the talk, more or less on time. And at this point, I would be happy to take any questions that you might have. Michael, I'll turn it over to you.
Sounds great. Thank you, Frank, for a wonderful lecture. I suggest let's do the question and answer session the same way as we usually do. So if you have a question, please type it into the chat box and I will read it out loud for Frank so that it all gets recorded. Just while everybody is sort of thinking of their questions and typing them in, Frank, maybe if you don't mind, I'll ask you a quick question. I've written down quite a few, actually. I thought that there was a lot of sort of thought-provoking things here. And that is, in the two major tests that you talked about at the beginning, where you have uniform states of uniaxial states of stress or strain, the split Hopkinson pressure bar, as well as the flyer plate, what are the maximum plastic strains that we typically expect to see when we do one of those tests?
Good question. So ultimately, what you find is that you are in the Kolsky bar test, you are limited in, I mean, ultimately these things are controlled by the striker bar velocity and the striker bar length. Okay, let me go here. So that's going to depend on the wave speed of the bars and the specimen length. If you want to get, I mean, in principle, you can get to very large strains if you make the specimen very short, because you can put some finite amount of displacement between these ends. And if you have a very thin specimen, then of course, your displacement, that's all of this stuff, divided by the specimen length, is going to be very large. So in principle, you can get to very large strains. The bigger challenge is to get to very high stresses, because that's limited by the forces that you can transmit through the incident bar and the transmission bar. Okay, and that's of course limited by yielding of those bars. There's also a limit on the strain rate you can achieve. This is the maximum displacement rate. And so again, the displacement rate over the specimen length will limit your specimen strain rate. Okay. All right. Now, but as a practical matter, you don't want to go to very short gauge lengths, because then you start to lose resolution. The displacements you're going to be measuring are going to be very small for a certain amount of strain. And so there are always compromises between the range of strains and strain rates you want to access and the fidelity of the results that you ultimately get. Okay? So what you want to do up front is calculations of this very type to work out what my strain rates are going to be, if I can launch my striker at a given velocity, what sort of strains might I achieve, and so on. Now, with respect to the split, the plate impact experiments, that's a bit more complicated because of the fact that you're working in one-dimensional strain, and essentially your volumetric strain is equivalent to your axial strain. Recall that the volumetric strain by definition is the sum of the principal strains. Two of those principal strains are zero, so your volumetric strain is just epsilon x. So you have to compress the material in order to get large strains. We normally think about solids as being almost incompressible, but in this context, they're not. Here, you have to go to very high pressures in order to get strains that are appreciable. By appreciable, I mean, say 5% or 10%. I think people have gotten to about 10% strain, but that requires projectile velocities that are in the kilometer per second range. Okay? So you have to hit these things really hard, really fast. And of course, you have to have a system where you can measure the back face displacements, or rather the velocities, accurately. Okay? And again, it's one of these things where before you do an experiment, you can do this type of calculation with some estimates of what this HEL might be. And there are various types of models you can use in extreme limits. There's the hydrodynamic limit of behavior. There's this elastic limit, and you can more or less construct proxy curves of this nature, and from them determine what sort of impact velocities you'll need in order to probe various points on the stress strain curve.
Okay, thank you very much. We have a question in the chat box from Bruce Remington. What are the lowest densities of foam that you can accelerate for impact experiments?
All right. We, in our work, have been, to some extent, so there's sort of two parts to the answer. One of them is what's commercially available. And I think we've been able to get down to about 8 or 9% using aluminum foams. Okay. Now, one of the challenges you're faced with is if you go with a very low relative density foam, then what you will find is that the yield strength will drop, and you run the risk when you're trying to launch this foam of actually yielding it simply through the pressures you're applying within your gas gun. Okay? And obviously you don't want to do that. But again, you can do these very rudimentary types of calculations in order to determine what the peak pressure should be in terms of a yield strength, knowing the yield strength is a function of relative density of a particular foam material, and this hydrodynamic term. Okay? You can also, just from geometry, work out the effect of the length of the projectile on the length of the pulse. And here you can look at the effect of relative density. So with a few of these basic calculations, you can determine what range of pressures and times you can access, and hence what range of impulse levels you can access. Okay. Now, there's no reason why you can't incidentally go to other materials. We've tried launching other types of foams. You can use various polymer type foams. They tend to be a lot weaker. They don't give you quite the kinds of pressures you can access with metal foams. Thanks for the question, Bruce.
I don't see any other questions showing up in the chat box, so I'm going to ask one more of my own. Oh, wait, we got one. So let me read the one from the chat box. From Jalen James, I have analyzed stress versus strain curves of split Hopkinson pressure bar tests in my research and have found that a different response can be obtained from nominally similar experimental runs. What contributes most to this varying response in stress versus strain for SHPB tests of nominally similar experiments?
Well, without knowing what the nominal exactly is, it's a little difficult to say, but one may be that
Maybe one way to rephrase it would be to say, what are the sort of typical pitfalls that an inexperienced experimentalist might encounter, which could lead to scattering results?
Well, one of the things to do is to check for whether or not you've achieved equilibrium. So you want to calculate the forces on the front face and the back face. You want to carefully look at the strain versus time traces to see the level of oscillations in those strains. There are naturally dispersive effects which occur in these kinds of bars. If you have a material that's of a low impedance, as I showed, you have other problems, and well, the problem is really one of equilibrium, where you get not only dispersion effects, but you have dissipative effects within the specimen. Assuming that your strain gauges are reliable, and that's the main thing, right? I mean, if the strain gauges are reliable and the system is well aligned, I mean, the system has to be, of course, very well aligned, then the results should nominally represent the range of real material behavior. Okay? And so one shouldn't rule out the possibility that variations in measurements are real. Okay? You have to be careful when you do any kind of experiment that you don't begin to rationalize, if you like, outliers, rationalize them on the basis of experimental error. Okay? You do want to look carefully at what your errors likely are and get some sense of how much that's going to affect your results, but also recognize that sometimes there's a good reason for outlying behavior. And so you don't want to toss out that data prematurely without thinking carefully about where that may have come from. Now, I should point out, if you're testing brittle materials, ceramics, for example, you will naturally get a much wider range of test results than you would if you're testing a metal or even most plastics. That's just inherent to the response of the material. Because with ceramics, the behavior is affected by weakest link statistics and so on, and those behaviors can be quite stochastic.
Okay, our next question is from Yupeng Zhang. For the dynamic experiment, given such a short time, how does the plastic viscosity affect the plastic response compared with rate-independent plastic response?
Can you just read that again, Michael?
Sure, and I'll rephrase a little bit. So when you look at the let's say the plastic front that forms in these experiments, can you distinguish between effects of rate-independent plasticity versus rate-dependent plasticity in that plastic response?
Is this in the context of a flyer plate impact or a
I think
split
it's
Hopkinson?
referring to either one. The question doesn't specify whether it's the bar or the plate.
Trying to distinguish between the rate sensitivity. Let me just go to. So I'm not fully clear on the question, but I will say this. If you want to understand the rate sensitivity, you of course would perform experiments of this type with different striker velocities, perhaps with different striker bar lengths, and in that way you can probe various strain rates. Okay? And so quite typically, people will report these kinds of stress strain curves at many different strain rates. And you can do these at various temperatures. You can do them at high temperature, you can do them at low temperature. The viscosity effects I'm not quite clear on. I'd be happy to cogitate on this a little longer if you want to email me the question, and perhaps we can have an offline discussion. But at the moment, I'm just, as I say, I'm not completely clear on the distinction that you're trying to make. Okay.
Okay. So can anyone hear me?
Yes.
I suggest let's pick this question up again on Thursday. Maybe give it some thought, and we can come back to it on Thursday.
Excellent idea.
Next question from Raj Kota. Can you comment on the impact response a given target based on projectile size relative? There's a verb missing there or something. Can you comment on the impact response of a given target based on projectile size relative to the thickness of the target? And I guess this is concerning the particle impact test?
Yeah. Okay. So let's talk about this in the context of the constrained impact type of test. Okay. This actually raises some really interesting questions about the nature of the damage. So let's take a look at this. Okay. So the experiments on the left were performed at different speeds and of a given projectile size. I think it was 6 millimeters or 8 millimeters, something on that order. Now, interestingly, you can actually, when you're analyzing problems of this type, actually get quite a long way using quasi-static solutions, using Hertzian contact mechanics. Okay? This can be used, for example, in calculating the maximum impact force at a given velocity, and that maximum impact force will depend on the projectile size. what you find is that there is, when you have a point load of this type of the type that you might imagine hit this point here, there is a critical force that's needed to create these so-called cone cracks. And so we've actually got, there's another paper on this where we've actually done analyses of the forces that are present at the contact site, and in particular, the maximum force that's obtained, and use that to predict the onset of cone cracking. There is another aspect to it, which involves the radial cracking, which emerges from the back face. So you can then again use a quasi-static solution to work out the hoop stresses that are present on the back face when you've got a rigid foundation subject to a point load up here. And again, you can work out, if you know the elastic plastic response of the projectile and the size of the projectile, and of course the impact velocity, what that force is going to be, the maximum force, and in turn, what the maximum hoop stress would be on the back face. Okay? So that's another game that one can play. If you understand the mechanics and if you understand the failure modes of interest, whether it's comminution directly beneath the impactor, cone cracking of this type, or radial cracking from the back, you can actually plan some of these experiments in an intelligent fashion.
Okay, we have another question from Bruce Remington. Would it be useful to study a ramp compression experiment on ceramics to high peak pressures and strain rates? For example, greater than 100 GPa and greater than 10 to the 6th or 10 to the 7th per second.
I suppose it depends on what it is you want to study. I think there is, getting beyond the Hugoniot-elastic limits and getting at shock speeds and the parameters and the equations of state. I think there could be interest in doing that for the purpose of studying phase transformations. Using flyer plate impact tests, you can indeed get to the pressures that are needed in order to induce those transformations. And in fact, I might even have an example of one here in my extra slides. People have been interested in this in a number of potential ceramic materials. Am I still sharing, Michael? Yeah, I see.
Yeah, it's still there.
So, I mean, this is an example of aluminum nitride. So the particle velocities here approaching 2 kilometers per second. This is somewhere in the the peak pressure is 35 GPa. It's in the caption. These are different thickness samples, I think. Yeah. And the interesting thing that you find in experiments like this is, down here, these represent the Hugoniot. And then you get other shelves in this particle velocity time trace, which reflect the phase transformations that occur at these higher pressures. So I can see there would be interest in potentially in materials like aluminum nitride, and I think boron carbide, other materials of that kind where there's some expectation of a phase transformation, which affects the if you like, the plasticity under very high pressures. That's the only one sort of feature that I think you can start to tease out going to extremely high pressures.
Okay, so then I will ask one last question. And this one is concerning the shape of the stress wave in the split Hopkinson pressure bar. So I understand that it is a uniaxial state of stress because the bar relaxes inwards or outwards, depending on whether it's a tension or a compression experiment. And I would, imagine that there's some kind of time scale for that relaxation to occur, and that might influence the shape of the wave front that is traveling down the length of the bar, even in steady state. Is that, am I correct in thinking that, or is that shape known?
You're spot on, Michael, in your question. So the oscillations you see here in strain rate are a direct consequence of these dispersion effects that you're referring to. So the magnitude of these dispersion effects will depend on the size of the bars that you're using. Effectively, what happens is when the striker hits the incident bar, it produces a stress pulse, which over a period of time, over a period of space rather, that's comparable to the diameter, has natural oscillations in it as these inertial effects kick in. That is, you start to get unloading stresses, relaxation stresses coming in from the outside radially, okay? And so that dictates some characteristic wavelength of these oscillations. Now, if you make the bars too small, which you might want to, if you want to reduce the frequency, or actually you did increase the frequency, you reduce the magnitude of these kinds of oscillations, you of course run the risk of not being able to transmit enough force to your sample. People have played games where you can, for instance, these dispersion effects become much lower if you use thin-walled tubes, because the inertia in that case is dominated by the thickness dimension of the tube rather than the diameter of a solid rod. Okay? So it's all in analyzing the dispersion at that contact between the striker and the incident bar.
Okay, thank you very much. And I don't see any further questions right now, so I think that at this point we will end the lecture. Thank you very much, Frank, for a very engaging presentation, and we look forward to the review session on Thursday.
Excellent, excellent. If anybody has any questions you want to send in advance, do so. It'll give you time to think about them. Otherwise, we'll see you again on Thursday. Thank you all for sticking around.
Bye-bye.
Bye.
See you.